we shall study the B plus trees in full today. As we have mentioned before, a B plus tree is an indexing scheme. It is a data structure for indexing any file based on a primary or a secondary key. We shall study it initially based on a primary key, and then we shall see what are the modifications to work on a secondary key. Effectively, a B plus tree is a balanced search tree. The operations insert, delete, and find required order of log n time each, where n is the number of elements or the number of distinct indices on which this indexing is done. Now, a B plus tree in a disk consists of two types of nodes: leaf node and internal node. A leaf node contains the key value and points directly to the block where the record corresponding to that key value or records corresponding to that key value are present. An internal node is a node which points to another internal node. It is used for finding elements and doing a binary or ternary type of a search on a tree. We shall see in details. All leaf nodes are at the same depth in a B plus tree. Each node is the size of a block. And another important condition is that each node, here when I talk of node, I talk of an internal node, is always at least half full. We will see the meaning of these one by one. In order to understand how we will proceed with a B plus tree, we will first study the structure of any node, and specifically the structure of an internal node and a leaf node. A node size, as mentioned earlier, corresponds to a block. So, because in a database the access is block wise, and if you want to access a record, anyway you are going to access the block corresponding to that record. So, you might as well have maximum information in one block. Now, depending on the size of the block, we can see how many records can be put in that block. For example, suppose 5 records can be put in the block. Then the node structure one, two, three, 4. This will contain one record. This will contain another record. This will contain the third record. This will contain the fourth record. This will contain the fifth record. and these will be pointers to other blocks. These records correspond to the key attribute or any attribute on which indexing is done. That is, they correspond to the attribute set the records take values from the attribute set on which indexing is done. In general and normally, when you do indexing on the key attribute, then the values of these records correspond to values of key attributes. The pointers point to other blocks in the structure. Now, suppose it contains, a block can contain only 2 records, then the structure will be like this. This will be one record R1, this will be another record R2, and now we will have 3 pointers, all 3 corresponding to different blocks. This is the structure of any node of a B plus tree. Now there is a slight difference between the properties of an internal node and the properties of a leaf node. A leaf node. Suppose this is one leaf node and the key value of a leaf node is 5. If the key value of a leaf node here is 5, here in the same leaf node, if I have another value, the value here must be greater than or equal to 5, greater than 5. It must be a distinct value which is greater than 5. So I cannot have 5 here and 3 here. The first condition on any node, whether it is a leaf or an internal node, is the values of the records or the key of the attributes on which indexing is done is sorted at least on a particular node. So suppose here it is 7. Now if it is a leaf node, then this pointer will point to the block. In general, we would expect it to point to the record, but it doesn't make any sense to point to a record, where the record corresponding to the attribute where the record corresponding to the attribute value 5 exists in the main or base file. So this points to the actual place in the base file. So this is an index file which we are constructing. There will always be a base file which may be sequentially ordered, and this will point to the block where the record which has the attribute value 5 exists. This will similarly point to the place where the record of attribute value 7 exists. And this will similarly point to that same place, and this will point to next leaf node in the B plus tree. That is, it will point to the next node in the B plus tree. So we will slowly see how the B plus tree structure is organized, then we will see how it is formed. I am just drawing up the leaf structure. Suppose there are only 3 leaf nodes. Then in this sequence on the leaf nodes, the records, the values will be sorted in the order of the attributes. This will point to the actual block where the record corresponding to the attribute value 5 exists. This will point to the block where the record corresponding to the attribute value 7 exists. They may point to the same block also if it is such a case. This will point to where 8 exists, this will point to where 10 exists, this will point to where 12, this will point to where 17 exists. Now, this is the base and the leaf nodes. All leaf nodes will be at the same level of a B plus tree. Now, a B plus tree will also have some internal nodes. That will be used for searching on the B plus tree. For example, in this case, we will have one internal node. Now, the internal nodes will point to either other internal nodes at a lower level, or finally may point to leaf nodes. That is, they will point to the blocks corresponding to leaf or internal nodes. In this particular case, they will be pointing to leaf nodes. Now, what will be the values in this record? The values here, the value here will be the maximum value at this site of the tree. In this case, the maximum of the two values is 7, so we will have this to be 7. The value here will be the maximum at this level, so it will be 10. Now, this will point here, this will point here, and this will point here. This value will be 7 and this value will be 10. And if this is all we have, this node will be defined to be the root of the B plus tree. Now, how will we search on the B plus tree? We will perform a variant of binary search. That is, we will first note that this value is such that all the records which are pointed to, that is the tree below this node, will have values less than or equal to the value of this. The tree below this pointer will have values which are greater than this and less than or equal to this, and the tree pointed here will have values which are greater than 10. That is the meaning of this. Suppose I want to find out a record of value 5, I will come here, compare 5 with this. If 5 is less than or equal to this, I will search here, then I will look at this, and looking at this I will get 5, I will move over to the block pointer and immediately get the value 5. If I want to search a value 10, then suppose I want to search a value 12, then I will compare with these two, it is greater than this, then I will compare with this, it is greater than this, so I will go along this pointer and then search. If I find 12, I will move along and go to the block. Suppose I want to find a value 9, it is greater than this, less than this. So I will move along here, look at this, and I will see that I cannot get anything here. So as soon as I see that I cannot get anything here, I will say it is something which that record does not exist. To simplify matters, you may also put in a tag value to identify whether a node is leaf or non-leaf. Either you put in a tag value or you know the height of the tree. If you know the height of the tree, then also, because all leaf nodes are going to be at the same level, so whenever you are going down, if you compute the height properly, you will always be able to find out whether it is a leaf node or not. The tag may be put for just easy programming, but it is not an essential item. There is another property of an internal node of a B plus tree. It is a property of most nodes, of nearly all nodes, but it is a major property of an internal node. And the property is this, that no internal node will be less than half full. When I say no internal node will be less than half full, I mean to say that an internal node with 3 pointers if it has got 3 pointers, then at most one of them can point to nothing. 2 of them must definitely point to a valid internal node or a leaf node. In general, if I have got 5 pointers or if I have got 4 pointers, then at most 2 of them can be null. The general rule is that if I have got in a record k pointers, that means I have got k minus 1 record key value attribute values I can put, then the ceiling of k by 2 pointers must be non-null. So if I have got 4, at least 2 must be non-null. If I have got 3, then 2 must be non-null, because when this is 3, 3 by 2 is 1.5, ceiling of 1.5 is 2. Because if this property is not ensured, then we will not get a balanced tree. Now we will see slowly how we form a tree by insertion. So let us see how we will form a tree by insertion. Before that, we can have a look at how a B plus tree of the same values of nodes would look like if I had got 5 pointers and 4 internal nodes. Possibly the B plus tree form will depend on the order in which the nodes are inserted or deleted. Alright, but suppose they are inserted in a particular order, then if we have got 4 internal nodes, this is one internal node. I'm sorry, I have just misutilized this space. I'll do it properly. Suppose I set up this tree. Suppose I set up this tree with 4 internal nodes. Now there are 5 pointers, and this can be 8 and this can be 17. Then this is not because with 5 pointers here I must have at least 3 pointers valid. This is not a valid B plus tree. In order to make it a valid B plus tree, I must have 3 pointers here. Now let us see how we will do insertion and deletion. We will take a case where we have got a structure, a simplified structure in which we have got 2 nodes and 3 pointers. So first let us insert a value 10. Initially there is nothing, so initially root is null. Now the next operation is insert 10. The find operation we know the algorithm for find. It is similar to a binary search. It will search on the attributes and then find. Suppose we do an insert 10, then a leaf node will be created. 10 will be put here. Though for a single value there is no need to create any leaf node. Actually you can simply put the root pointing to the block. The root will point to block where the record exists, because that is the only record. The root, this will point to the block where the record exists. Now suppose I insert 20, then this will point to 10, this will point to 20, this will be ground, and this will now be the root. This will point to the record where 10 exists, this will point to the record where the attribute 20 exists, and this will be null, this will be a leaf node, this will be root. Suppose I give insert 25. Now 25 will be put in the actual base block. Similarly here, when it is put, it is going to be put in the actual base block by the normal. If the base file is a sequential file, then insertion there will continue as in sequential mode. Here the index file will be updated. Suppose I give insert 25. Now the block, you will search this, you will see here, and now you will have to put 25 after 20. So you will look at 20 and put somewhere at the end of the file 25, and you have to update this index record. When you try to update this index record, you see that it's a leaf record which is already full. In case a record is already full and you want to insert into that record, the operation is split the record into 2 records. That is, create another record and redistribute the elements. Here 25 is to be inserted, so this will be the original one, 25 will be put here, this will be made null, this will be made null, this will point to the place where 25 points, this pointer will be made here, this will be made here, this will point to 7. So this is the insertion at the leaf, but now which one will be made root? For this, since we have a tree, we must have a unique root. So we will, and since the root itself has been split, you have to create a new root node. So we will create a new root node, make this root, this value will be 20, this value will be 25, this value will be null, this will point here, this will point here. This is how the structure will be created. Since we try to insert 25 here, we fail because this is already full. We split it. We split it into two, reorganize the nodes, reorganize the elements at the nodes, and then since we have split the root, we will form another new root and make the pointers work this way. So we had a situation where we had this structure, we had this structure. Suppose we want to insert 30, then it is very simple. We will see whether 30 will be inserted this side. No, we will compare. We will first find 30. To insert any node, we will have to first find, because suppose it is done on an attribute which is not a primary key, then corresponding to that same attribute, more than one record may exist. If more than one record exists, then we will have to find where it exists, and on that chain of pointers, we will have to put it at the end. On the bucket of pointers, we will insert it and we will have to make it on the bucket. But suppose it is on the primary key, then only one record with that value will exist. So if we want to insert 30, we will first see if 30 exists. If 30 does not exist, in this case 30 is very simple, you put 30 here. So if we put 30 here, I am not doing it, but if I put 30 here, then this will point to 30 and this value will have to be updated to 30. So the step is insert and then revise the values of these internal index values up along the tree as you go. And this is the root. Now let us see what will happen if we try to insert a value 15. We will come here, compare, see 15 exists here. Once we see 15 is supposed to exist here and does not exist, 15 has to be inserted here. But this is full. So once a node is full and you want to insert something into that node, then that node will have to be split. So we will split this node up. After splitting this node, that is, we will generate another node. Instead of this node, we will replace it by two nodes. That is, we will actually allocate one more node structure. Once we allocate one more node structure, we will redistribute the values. Suppose this is the original one, then 10 will be here, 15 will have to be put, so 20 will be shifted here, 15 will come here, this will be pushed here, this pointer will now point to where this one was pointing, this will not exist. This is the structure we have after splitting this node, and then we will insert these two here. This was originally existing, we will have to insert this here. So this value, once we try to insert this here, then we will see that we are exceeding the quota of this as well. I am sorry, we are not exceeding the quota of this. We have to point, we have one free pointer available here. So what we will do is, this one will lead to a value 15, this one will lead to a value 20, and this one leads to a value 30. So we will point this here, we will point this here, and we will utilize this free pointer to point here. And the structure after the whole thing, that is, initially we had this structure. Let us draw both of them, and now we will see what was the initial structure and what is the final structure. We had 20, we had 30, this is the structure which we had, and this was the root. We applied the operation insert 15, and after doing all our modification, we reached this structure. The structure that we have reached, we tried to insert 15 here, we split this into 2 and we got 2, we pointed this here and then we tried to insert it here. Now trying to insert it here was easy because we had a free pointer. Whenever you have a free space, you can easily insert one new node. But if this was also full, then we would have had more problems. But in this particular situation, that is not the case. So this is not full. So we insert this, we update this here, we update the maximum value here, and we point this here. This is the structure that we get if we insert 15. Now the last phase is, here the root was not full, so it utilized the pointer, so the root was neither split, so we did not have to generate a new root. Finally, at this point, let us try and insert another new node, and let us try and, if we insert a node 22, it is very easy. We will insert 22 here and we will update this to 22. But suppose we have to insert a node, say 35, then there are various options that we can have. A complex option would be to shift this 25 here and put 35 here and update these. For that, you would not only need the next pointer, you would have required the previous pointer as well, or you come here and you look at its brothers as well. But a simpler strategy, which would still maintain the order n complexity, would be to insert it directly here. How would we insert it directly here? We will insert 35 here, split this up into 2. And in one place we will put 25 and 30 and another one 35. So we will split this node up into 2 nodes. In another one we will put 35, ground this, these will point, instead of this we will replace it by this, we will make this one point here, this pointer will now point here. But then we will try to insert this here. Once we try to insert this here, we will see this is full. So we will now split this into 2. we will split this into 2 and redistribute. In one there is 3 and there is 2, so we will put 2 each, because in our methodology a node must be always half full. We cannot put 3 in one and 1 in the other. We will have to distribute 2 each. So these 2 we will put here and these 2 we will put here, and then we will redistribute and generate another new root node. So now we will ground this one, we will make this one point to this node, this one point to this node, ground this, this will become 30, this will become 35, generate a new root node where this will become 20, this will point here, this will be ground, and this side will be 35. I will redraw the whole thing so that it is easier to see what has happened. We had a structure like this. We had a structure like this. We inserted 35, we split this up into 2 and we generated one new leaf node. So in the leaf level we now had we did not touch this, nor did we touch this. A sophisticated algorithm may touch this, but instead of this one we generated 2. Here we put 35 because 35 comes later on. If we had inserted 26, then 30 would have moved this side and 26 would have come here. But in this case that is not the scenario. So this is what happens at the leaf level. And when I insert this, this one is split into 2, and therefore we generated 2 more here, this one, and redistributed them 2, 2. We split this up because we had to insert one more node here. We split this up and redistributed it 2, 2, the smaller 2 this side and the larger 2 this side. So the smaller 2 comes here and the larger 2 come here, to ensure that always 2 pointers are always available. Otherwise one would be 3 pointers and one would be 1 pointer, which is not allowed in a B plus tree with 3 pointers. This would be 15, this would be 20, this is null, this is 30, this is 35, this is null. Now since we have split the root, we will have to have a new root. This would be the largest this side, which is 20. This would be the largest this side, which is 35. And this would be the new root. So this is how we do insertion, and since in a tree which has got 3 pointers, there will be at least 2 pointers. The height of the tree will always lie between log 2n and log 3n. Log n to the base 3 will be the minimum height that it can have, and log n to the base 2 will be the maximum height that it can have, because either 2 pointers will be there or 3 pointers will be there. And if you notice that an insertion operation requires a find which is log n, and then split and move up only along the path of the tree, therefore it does not require more than order of log n operations for performing an insertion.
Can we follow this method for insertion and at a later time do the compactation to the other methods?
Compactation to any of the other methods, this is a compacted structure anyway.
To become minimum.
For the leaf nodes to become minimized, then what we can do is we can move along and just pack up like this, and then we have to form the tree from the bottom. Forming the tree from the bottom, given the leaf nodes and forming the initial B plus tree, will take order n time. Because for a tree with n leaf nodes, there can be only n minus 1 internal nodes. A tree with n leaf nodes can have n minus 1 internal nodes. So when you form the initial B plus tree, then what you do is you pack this up fully and then take them 3 by 3. Suppose here it is 3 by, take them 3 by 3 and just ensure that the last one does not become 1. Just ensure that the last one does not become 1. So take them 3 by 3 and the last one you may take 2 by 2, because if it ends up with 4, here it is 4. So when you see 4 leaf nodes, though here you could have packed this here and these two here and you would have got 3 leaf nodes. In this case you would have packed it up to get 3 leaf nodes. But suppose this was full and this was full, then you would have got 4 nodes. 4 nodes you cannot form 3 and 1, you would have to form 2, 2. So when there are empty spaces in leaf nodes and when you compact the whole thing, then you will bring 25 here, 30 here, 35 here, and then tree will go down. Obviously, when you compact, you make it fully packed, and the algorithm for compaction is order n time, because you will have to do this, pack these up, then set these up, set these up. You just go in a bottom up manner, you will solve it. There are n leaf nodes and n minus 1 internal nodes, so n plus n minus 1 will be the total number of nodes which you will have to work on. We will tackle delete next.